So from section 5.5, we have just a few more ideas. Now check out this definition here. It says a series A sub n exhibits absolute convergence if the series, the absolute value of A sub n, converges. A series A sub n exhibits conditional convergence if the series A sub n converges, but the magnitude or the absolute value of the A sub n of the series diverges. So we're just going to play around with these two ideas. So take a look at this series here. N equals 1 to infinity of negative 1 to the n and 1 over n. Now this is what we call the alternating harmonic series, and remember we did a test on this previously. So this here we know converges. But let's take a look at the absolute value of this. Okay, and that's what we're dealing with right here. So then this is going to equal the series n equals 1 to infinity of 1 over n. Hopefully that's okay with everyone. Now if I look at this series here, this series is actually the harmonic series. And we know this diverges, don't we? And why do we know why it diverges? So this diverges because it's a p-series and p is less than or equal to 1. So we know this diverges for that reason. So therefore, the original series is n equals 1 to infinity of negative 1 to the n of 1 over n converges by the alternating series test, which we did previously. And the absolute value of this series, which is here, diverges. So look what this is saying then. So this series converges, and that's the original, and the other one here diverges. So that essentially tells us that the series n equals 1 to infinity of negative 1 to the n, 1 over n, has conditional convergence by definition. Okay, so that's just one way I can show you how this definition actually works for us here. Okay, now I'm going to talk about this next theorem that we have, which I think is very difficult to talk about right now because this is dealing with stuff that we're going to see more in the next section. Here it's a little bit forced. So let's just take a look at this. So this says if the absolute value of A sub n, the series of that converges, then we can say the original series that we had converges. But we're actually going to talk about this in the next section. But I wanted to bring it up because it's in this section. So now I went to the homework set, and this was one of the series that I actually seen, and it was actually the first one. It was number 250. And this was the series. Oops. And this is n equals 1 to infinity of negative 1 to the n plus 1 to the n over n plus 3. Now when I look at this, the first thing you think of is, because the way the series looks, is the alternating series test. But if we look at this, and we look at this first condition here, that has to be decreasing. And also, the limit of b sub n has to equal 0. So for this one, I'm going to pick the second condition because that's easier to see. So all I have to do here is take the limit as n goes to infinity of n over n plus 3. And what I see here, this is going to be infinity over infinity, so this is L'Hopital's rule. So that tells me I can take the derivative of the top over the derivative of the bottom. So that's going to give me 1 over 1, which equals 1. as the limit. So there it is. So that is not 0, which the second condition implies I have to have a 0 there. So therefore, I can't use the alternating series test for this. And this is strange because they fill this whole section up with a bunch of these types of problems. Now, the way we can work this out is think about the divergence test. This is really what we're dealing with here. So if I take the limit of this thing as n goes to infinity, do you guys remember what the divergence test was? So now with this divergence test, essentially, if we look at this, as long as our limit is not equal to 0, then we can say the series diverges. And that's what we're going to focus on with this one. Only because the homework is full of these. So now, what I want you to see here is I just want to talk about this piece right here. So if I look at this piece right here, I did the limit just above there, so I know it's going to equal 1. At least for that piece. So I can say, hey, this piece is 1. Now again, I'll have to do the limit like we did above, but that's going to give me 1. So if I look at the limit of this, this is really just going to be an alternating, because if I look at this piece right here, this piece right here alternates. So I'm going to go -1, +1. So essentially, what I can say here, once I show that that limit is 1 there, or whatever it is, then I can simply say that this just does not exist. And then if it does not exist, what does that tell me here for this divergence test? So then it says if the limit is not equal to 0 or the limit does not exist, then the series diverges. So right away, I can say this implies by the divergence test. And I'm just going to write dt. I would have to write the original series out, though. N equals 1 to infinity, -1, n plus 1, n over n plus 3 diverges. So we don't even use any of the information from this section. This is kind of what gets to me a little bit, but it's okay. So this is kind of what it turns out to be here. But this is an alternating series, don't get me wrong. It is going to alternate terms there. It's going to be positive, negative. So it is going to give me that, but I'm not using any of the alternating series test or any of those things here. Just the divergence test, which is the first thing we learned. So just something to keep in mind as you go through the rest of this section. We're going to talk more about that next theorem in the next section. So here we go.